Well, welcome. This is the next further Pure 1 FP1 video. This is we're getting halfway through now. This is the second numerical solution to equations f of x of a function of x equals 0. This particular way of solving them is called the linear interpolation method. Almost said the first one then. Wouldn't have been very good to call it the other method and start confusing you. What I've drawn on the left hand of the board here, I'm not sure if I mentioned this in my last video. If I didn't, I'll just go through it now. I think it's probably a good idea to recap it anyway. So we've got this cubic equation on the board here. Now, in this question, we're told that it's between 0 and 1. Don't worry, I'll get into the new method in a minute. There's a solution that lies between 0 and 1, and I emphasise this number line idea. Where you just shaded in the bits. This is getting really primary school, but whatever. Shading the bits where so you have the range, and then you look where the change in sign over which range has the change in sign. Kept narrowing it down, and then we were left with the ranges between 0.75 and 0.875, and then you see which. So you halve that, and then seeing which half. So is it below 0.8125, is it above 0.8125? It changes sign, and it was below, so therefore it was close. It was between 0.75 and 0.8125, so therefore when we rounded it we got the solution to be 0.8. Okay, so as I said, I think I went through that in the last video. Just recapped it there. That's the method we would have done if I'd have not done it in the last video, but I'm pretty sure I did. What we're going to introduce today in this video is we're going to be looking at the linear interpolation model. Now, you could have answered that question in either way. That's why, look, I'll split the board up. Coincidentally, might be showing the same question, and I might be a little bit crazy, and I might need to get alive as well. All of them things have yes attached to them. So, what we're going to do is introduce this new method. So what the hell is it, first of all? Well, the idea of linear interpolation is, well, as I said, if you've done statistics, this is just bringing up random crap to be honest, if you've done statistics you will hear interpolation and think, interpolation, we did something like that in statistics, but no, it's nothing like that, because this is further pure. This is not statistics, they're different things, but I just put it in there to confuse you, just to highlight they are not the same thing. This interpolation, linear interpolation, is all about comparing similar shapes. So you may need to revisit your topic of similar shapes, but as I said, you don't really need to understand them at all actually. Just the only thing you need to understand is they have the same angle, but I don't think it's really relevant to working out the question. You just have to understand they have the same proportion, and it might be a little bit of a good idea to have a refresh on what they are. As I said, I think there's a video on YouTube somewhere about that, but big time for that. So anyway, as I said, I didn't really remember what similar shapes are whatever, when I started looking at this topic, but it comes across a very apparent. There's a method, just like there's a method for this, there's a method for the linear interpolation. There's no formula. There is a formula in the next and the last numerical solution video that I'm going to do for further Pure 1, but for this numerical solution, as I said, it's just kind of a method similar to this kind of thing where there's no formula to follow. Okay, so as I said, it's all about similar shapes. So there's nothing that we can draw apart from the graph. Okay, so we'll just draw the graph y. No, don't copy this just yet. So y x. Right. So what I'm going to do is label on the 2 points that we know, the two extremes. So you might have done this, but if you said the limits are between 0 and 1, 0 and 1, and we said okay, at 0, x is 0, and we've got a y value to be -2. So we just put that on there. So put that -2, and then we know our next value is where x is 1, y is 1, so just put 1 here, and then it's something like that. Now, in the interval bisection, I don't think we actually drew the graph on. Now, normally you would associate the graph of x cubed to look something like this. I don't know specifically what this graph looks like, but we know 2 points, and we know it could do this, or whatever, we don't know. However, I mean, we could do, and it'd take ages to work out, and then you'd be like, okay, well, what's the point in actually doing this method in the first place if you're just going to work out the entire shape of this graph? Now, we know they join these 2 points. That's all we know about this graph. So that's all we're going to do, just join these 2 points up with a straight line. Okay. Now the reason we're doing this is because obviously we don't know the proper equation of the curve, and it is quite hard to kind of see. I really, well, on my book it was a lot simpler because it had a ruler, so I'm just going to try. Probably should have tried that before, but whatever. So just draw the 2 points on and then try and connect them up with. Sure. I'm not sure I really had one, to be honest. So the board rub is just going to have to do. You get the idea. Okay, that's all right. Okay, so what were we talking about? How can we create a similar shape from this? Well, similar shapes are the same shapes at the same angles, and the ratio of the sides are the same. So the ratio from one side to the other would be the same as the ratio of the lengths. Okay, so the only thing we can draw in here is triangles. So we'll draw triangles. Okay. I'll label the left-hand side triangle A, the right-hand side triangle B. Okay, so the left-hand side triangle A goes from from 0 minus 2 to 0, 0. I'm going to call this where it intersects, we're going to call it alpha. And that's because it's an approximation. It's not the certainty like we could do here. It's the approximation. We're going to get to this certain value, but that is what we call the approximation. And then the B one goes from 0 to 1, 1 to 1, 0. Okay? Alright, so they're similar shapes because they have the same angles, etc. Okay, because these two angles are the same, they both have two right angles, and therefore, because they both obviously both triangles, these two angles must be the same as well. So therefore they must be similar shapes. That's why we can assume that. Okay? And that's because of your, I don't know, some angle thing that you did in year 9, I can't off the top of my head remember, and it doesn't matter because you don't need to work out the angles. Okay, so what are we going to actually do with this? Well, as I said, the similar shape. So we know the height of this, therefore, is 1 because it goes from 1, 0 to 1, 1. So it increases in height of 1. This has got a height. I know it looks like a depth. Necessarily we would call it depth. It's got a depth of 2. Now, not minus 2 because you can't have a height of minus 2. So, and that'll become apparent when we start looking at, there's something you could easily get confused on in this kind of question. Now, the lengths of each of these ones, so the length of A, we know this is 0, we know this is alpha, we don't know what alpha is, but obviously we know what 0 is. So, what this is, it's alpha take 0, so it's just alpha, in other words. However, the length of the B triangle, what I've called B, is 1 take alpha, because we know that the end point of B, so where it ends, is as an x coordinate of 1. Where it starts is where the x coordinate is alpha. Okay, so it's something like that. Okay. Now we're just going to go on with our idea of similar shape. Now we said the ratio of the height is equal to the ratio of the lengths. Okay, so therefore we compare the height of triangle. We do the height of triangle B over the height of triangle A. So it's 1 over 2 because the height of triangle B has a height of 1 and the height of triangle A has a height of 2, and that's equal to the lengths of the two. So it's the length of triangle B, which is 1 take alpha, over the length of A, which is alpha take 0, or in other words, just alpha. Okay, so now we can expand this out and simplify it down to work out what alpha is. So we times both sides by alpha, times both sides by 2, so it becomes alpha equals 2 brackets 1 take alpha. Expand the brackets out, so therefore we get alpha is equal to 2 take 2 alpha. Add 2 alpha to both sides, so we get 3 alpha is equal to 2. Divide both sides by 3, so therefore alpha equals 2/3 or 0.6. Recurring. Okay, now that's just an approximation. That is the base of this alpha is an x coordinate where it intercepts. Now the equation of both of these curves is exactly the same, so x cubed plus 2x take 2. Now if you put x to be 2/3 into that equation, that is obviously that's obviously not what it is, it's 0.8. So therefore it's not what we want, okay? Now in this question, I should have mentioned it before, we're asked to do linear interpolation twice over. Now the reason I mentioned it there is because we've done it once over. Basically, we've found this approximation, which is when you find that, you've done a linear interpolation. Do it again, find another linear interpolation. They call it twice over. Now, I kind of said this was almost similar to that irritation thing, change of sign. This is also similar to that kind of irritation thing as well. Because that irritation thing we did in C3. Now, if you haven't done C3, please just ignore me. But it's the benefit of them people who are picked up AS further maths in their second year, and are just, it's easy to compare it to different things. We're going to go into parametric functions later on in further pure, and we can link that to a bit of C3 as well, or C4 or whatever. Anyway, so what I'm trying to say is this is just an x value, and we're going to keep doing this until we find a well, okay, so this is our x value, and now bearing in mind we didn't know all of this, we'd put that x value into f of something, into the function, so it'd be the function of 2/3, okay? So you put 2/3 into the equation, so it'd be 2/3 cubed plus 2 times 2/3, take 2, okay? And if you were to put that in your calculator, you should get a value of exactly negative 10 over 27, okay? Which obviously is a negative value, therefore that y equals negative 10 over 27, hence it hasn't crossed the x-axis, hence the intercept has not yet occurred, as we know from this side. Okay, so obviously we're going to need to do it again. So we do the same principle in terms of we draw the same kind of graph, but just like we've done over on the interval section, we don't bother with the area. With the side we know is already negative because it's not going to be over that side. Now we know it's greater. We know x, the intercept must be greater than 2/3 because it's kind of an increasing function, not a decreasing one. So it's not going to be on the left-hand side of x equal to 2/3. So therefore, we're just going to assume this. Now we know what y and x is when x is 2/3, we know what y is. It's negative 10 over 27. So we can draw that point in and kind of use that as this starting point here. Okay, it'll become apparent when I start to draw it. Okay, so we draw the axes again. So coordinates of y and of x. Okay, so instead of drawing when x is 0, we've got y is negative 2. We're going to draw x as 2/3 and put the point as being 2/3. Sorry, my door's just going to slam if I don't close it properly, so you just have to give me. Sorry. Sorry about that. Yeah, it does slam, it scares me to death sometimes. You know, just sat there revising it. It's the convection coming. Oh, some physics. Interesting. Anyway, so go back to this actual maths we're going to be doing. Right, so as I said, we put before when x is 0, y is 2, but we know it's not going to be on the left-hand side of x is 2/3. So we draw sort of a new approximation on knowing this. Okay, so put where x is 2/3, and you put a little line down saying, okay, well at that point we know y is negative 10 over 27, but we know it goes through a point. We're going to call this approximation 2 or alpha 2, and we know when x is 1, y is 1, 2. Okay, so this second triangle hasn't changed. Okay, now we're going to do the similar triangle thing again. So that's 1, 1. I'm going to call these two new triangles C and D. Okay, D being the original, D being this one, and C being a new version of this A triangle that we've sort of moved over to the left, to the right even, whatever. Okay, so it's the same kind of principle, the height of D over the height of C, and the length of D over the length of C. Okay, so the height of D hasn't changed, or height of B, whichever one. I think we're looking at this one. Okay, so it's 1 over the height, which is 10 over 27. It's not negative 10 over 27, remember, because we can't have a negative height. Now you could do that just equal to 27 over 10, but it's always nice just to keep with the same kind of pattern so you're not losing track of where you are. Okay, and then that's equal to the length of D over the length of C. Now the length of D is the same, it's 1 take alpha. Now I put little subscript 2. You can just do 1 take alpha, but the fact we've already done 1 take alpha over here, I think it's nice to start, like, because it's a second approximation, it's nice to put the little subscript of 2. Just be careful not to get it confused as 2 alpha, but you know, it's just something else to think about. And then for the length of C is just alpha subscript 2 or alpha take 2/3 because we know the x value is 2/3 and that's the length. Remember, we're not looking at the height. Alright, and then it's just a case of rearranging this and simplifying it like we've done over here. Now, we're hoping you can just, it's just a case of doing 1 over that, which is get 27 over 10, times in both sides by alpha, take 2/3, and simplifying it down. I don't quite have the room on the page to do that, but then you would get 37 alpha over 27 equals 28 over 27. Okay, times both sides by 27, so therefore 37 alpha is equal to 28. Divide both sides by 37, so therefore we get a value for alpha 28 over 37, which is 0.756. And because when we put f of, basically because we've been asked to do it twice, we have to round this up to, and it's asked to 1 decimal place. Therefore, the alpha is 0.8, as we predicted over here. Now, generally, we'll tell you use the second approximation or third approximation, or whatever the exam might be specifying. However, if you put f of 0.756, you would actually end up with a negative value, but it'd be so small that if you were to do anything bigger than 0.8, you would get a positive. Okay, so as soon as you hit 0.8, I mean, you could carry on doing that. You could go on and on, keep doing this method of creating a new triangle for C, and you would make the triangle smaller and smaller and smaller, so then you would end up with pretty much like 0.7999 or whatever. But because we're rounding it up to 1 decimal place, you can see it getting higher, and also it's only after 2 irritations, so you just round whatever alpha value you get at the second irritation, well, say irritation. The second step of this, so what the second attempt at linear interpolation, you would round up to 1 decimal place if that's what it asked. Generally it would be 2 or 3, and it will always really specify. So that's kind of where you would go. Alright, now there are some questions. It may say, you know, just find the root, where you would continue doing it until you got positive. So basically you would find this value for alpha. It might not be in your second, it might be in your third or fourth attempt at doing this, and then you would sub it into the equation and you would get something, some value for y, and now if that y value is extremely small, like minus 0.05 or something like that, then you would just round that value up, or you would continue doing these interpolations until you get a value for alpha, which is the x-intercept thing. And when we put it into the equation, we get a positive value for y, and then the first one to do that, the first alpha to give that correct positive y value is the approximation for the intercept. Okay, now that's pretty much the summary of both of these two methods in one video, which I think is quite good. Now the question that the reason that I mean, as I said, these questions are quite kind of standard. I'm more than happy to do a few others, but I just need to have my work through clarified. I just need to, basically I need to clarify my answers. Obviously I do that, just to make sure I've not gone completely insane, because I think I've done a bit of a mess up on one of the questions I've attempted that I was going to put in this video. I mean, it's pointless me telling you, I could have just not told you. But I was going to put another question in this video, but I kind of messed it up a little bit, and I think if you can understand that, that's a lot easier than doing this other question, which will just confuse you. Like I tried to include that other question in my last bisection video, which I made a bit of a hash of. So I don't want to have that done again. So anyway, thanks for watching. Hopefully you've understood that. Really, I mean, I could read out this other little sheet that I've got, but really it's just a case of using the similar shapes, comparing the heights. The height of one triangle over the height of the other equals the length of one over the length of another. Simplifying it down to get a value for alpha, putting it into the equation, because that value for alpha is approximation for the x-intercept, and then if we get y to be, if y was originally negative, if it just, we keep doing this approximation thing until we get a positive value for y, or however many irritations, or not irritations, how many interpolations it asks you to do, and then you would just round it up to whatever it, that's in 1 decimal place, 2, whatever. By the way, if you're not sure, if it doesn't specify to what decimal place, always do it to about 3 significant figures is always the key one to stop at. Okay, so hopefully that's been of some help. Sorry for waffling on for far too long, as I normally do in these maths videos and every other video that I do and put on YouTube. So thanks for watching, and we'll see you in the next video, which should be the last numerical methods one.